You have a long, messy digital logic equation, and you need to simplify it. To do that, we have to organize those abstract mathematical statements into a physical space. This physical space is the Karnaugh map, or K-map. It acts as a bridge, letting us plot both sum of products, which are equations adding together multiplied variables, and product of sums, which are equations multiplying together added variables. This image shows two ways to set up a four-variable K-map. Before plotting any math, you must decide where your higher-order bits, A and B, go. The left map places them across columns, while the right places them down rows. Locking in this orientation is step one. Once your axes are set, every mathematical term in your equation will have a specific, unchanging physical address inside this grid. This chart shows how to map a list of minterms, specific combinations of variables producing a true output, creating the onset. When given a list of minterms, simply place a 1 in each corresponding cell. This chart shows the exact opposite, mapping a list of max terms. Max terms represent the offset, which are variable combinations that force the output to 0. For these, place a 0 in the corresponding addresses. Identifying whether your starting expression represents the onset or the offset dictates your entire process. It tells you immediately whether you are filling your grid with 1s or 0s. Now let's move from simple lists to full equations, starting with a canonical sum of products. Canonical means every single variable, A, B, C, and D, appears in every term of the equation. This canonical SOP expression contains all four variables in each term, translating directly into specific minterms like M0, M5, M10, and M15. You finalize the map by placing 1s into the exact cells matching those minterm addresses. We follow a parallel process for canonical product of sums equations. But instead of minterms, these POS equations target max terms. For POS equations, max term expressions can be confusing. Instead, apply De Morgan's theorem to convert those max terms back into the complement of familiar minterms. Because the first term converts to the complement of M15, we place a 0 exactly at cell 15. Canonical equations are straightforward. Because they contain every variable, they offer a clean one-to-one translation straight to a single cell on the map. Things get more complex with non-canonical equations. In these expressions, terms are missing variables. Instead of pointing to one specific cell, a term with a missing variable maps to multiple cells simultaneously. This image illustrates mapping the first term, A and not D. Because B and C are missing, we look for intersections. We highlight the bottom two rows where A is 1 and intersect them with the outer columns where D is 0, giving 4 cells. This image shows the next term, not A and B and not C. We find the single row where A is 0 and B is 1, and intersect it with the two columns where C is 0, creating a tighter group of 2 cells. This chart shows our final term, B and C and D. We find the single column where C and D are both 1, and intersect it with the middle 2 rows where B is 1, forming another group of 2 cells. This grid shows the final result. All 3 distinct groups are plotted together, filling the K-map with our complete onset. Here, a missing variable behaves like a broad coordinate. It assigns entire regions of the map to a single value, instead of targeting individual cells. The final challenge is mapping non-canonical product of sums expressions, which requires one extra step before plotting. This table demonstrates that step. First, we expand fragmented sum terms by adding missing variables, generating canonical max terms. Next, we use De Morgan's theorem to translate those into canonical minterms. Finally, we map zeros into those exact cell addresses on the grid. By systematically expanding fragmented logic expressions into a canonical structure, they map perfectly. You now have the framework to untangle and plot any Boolean equation.
Thanks for watching. See you next time.